In this video, we are going to discuss the Laurent series. This is our overview slide here, which we'll spend about 5 minutes on before going over each topic in more detail. The Laurent series is related to the Taylor series we discussed in our previous video, whereas the Taylor series requires a function to be analytic at a point z0. We can use the Laurent series even if that's not the case. So if a function fails to be analytic at a point z0, one cannot apply Taylor's theorem at that point. It is often possible, however, to find a series representation for z around z0 involving both positive and negative powers of z minus z0, and that is exactly the Laurent series. Our Laurent series theorem then says, suppose the function is analytic throughout an annular domain where the distance between z minus z0 is greater than r1 but less than r2. And this is our illustration here. Remember, the idea is that the function might fail to be analytic at z0. So the idea is we're going to kind of make a little circle of radius r1, which we can make arbitrarily small to surround the point that we're not analytic. And then we say we do have this annular region here between r1 and r2, so I'll shade that in yellow, where our function is analytic. And then z minus z0 is in this region here, in the annular region. And then c is going to be our curve. So c denotes any positively oriented simple closed contour around z0 lying in the domain. So here is an example of a contour c that is positively oriented. It's around z0, but it is contained entirely in the analytic region, this annular region here. Then at each point in the domain, so every point in this annular region, the analytic domain, f of z has a Laurent series representation, and it's given by this formula here. We have f of z is equal to summation n equals 0 to infinity a sub n z minus z0 raised to the n plus summation n equals 0 to infinity b sub n divided by z minus z0 to the n. So you can see here we have the negative exponents of z minus z0, and here are the positive exponents. The part with the positive exponents is called the analytic portion. If the principal part is equal to 0, what we're left with is the analytic portion, which is actually the Taylor series. When we have this principal part, that's when we have a Laurent series. Here are the two formulas for the coefficients. For the analytic portion, the coefficient is a sub n, which is equal to 1 over 2 pi I, the closed curve integral of f of z dz divided by z minus z0 n plus 1. For the principal part, the coefficients b sub n is equal to 1 over 2 pi I integral, closed curve integral of f of z dz, z minus z0 over raised to the minus n plus 1. For our first example of a Laurent series, we're going to replace z by 1 over z in the Maclaurin series we had derived in our previous video. That was e to the z is equal to n equals 0 to infinity of z to the n over n factorial. And when we replace this z by 1 over z, because remember this formula is good for any complex number z, so it's certainly good for 1 over z. So when we replace 1 over z here, we get e to the 1 over z is equal to the summation of 1 over z to the n, which is this portion, and also 1 over n factorial. And then we can multiply it out, and we get 1 plus 1 over z plus 1 over 2 factorial z squared plus 1 over 3 factorial, etc. And much like we did in our previous video, we're going to be using our Maclaurin series expansions to find other representations. So here are the two formulas we used. We had this Maclaurin series e to the z, and we also had the Maclaurin series 1 over 1 minus z. We also had the formula for sine of z, which is e to the iz minus e to the minus iz over 2I. And we found in our last video the Maclaurin series for that is negative 1 to the n, z to the 2n plus 1 over 2n plus 1 factorial. And then we did term-by-term integration to find that cosine of z's Maclaurin series is 1 minus 1 to the n, z to the 2n over 2n factorial. So these are worth remembering. And we would start with a form like, well, we would start with something we wanted to convert to a series. We would pick one of these forms that most closely resembled it, and then we would do manipulations to these formulas until we had a series representation of the expression we wanted to make a series representation for. And the things we could do is we could take the z and replace it with a simple function of z, like 3z, or in this example above, we replace z by 1 over z. Or we can multiply the entire equation by a value, both sides of the equation, or we could do term-by-term differentiation, like we did for the sine and cosine, and we can make adjustments to summation indices. I really wanted this example to be on my overview sheet, but it is quite long, so I could only put part 1 of this. This problem breaks up into 3 parts. I could only put D1, the D1 part. And even D1 is sort of involved, so I'm going to give you a really quick overview, and later in the video we'll go over this in more detail. But the problem is to find the Laurent series expansion of f of z equals minus 1 over z minus 1 times z minus 2. The first thing we do is when we look and compare it to our forms, it doesn't really look like e to the z, and it certainly doesn't look like sine or cosine, and the closest thing it looks like is this 1 over 1 minus z. It's essentially a polynomial over a polynomial. And the first thing we're going to do is try to break this up using partial fractions. That's an algebra technique. We'll go over it in detail. But we can say that f of z is equal to 1 over z minus 1 minus 1 over z minus 2. As I said, we'll go over partial fractions in more detail later in this video. The next thing we want to note is that f of z has 2 singular points, z equals 1 and z equals 2. In other words, that's where we're in danger of not being analytic. So we have to separate out our domain so we avoid these singular points. That's why we have 3 parts to this problem. The first part is our domain where z is less than 1. The second part of our domain is when z is between 1 and 2, and the third part is when z is greater than 2. And again, we're trying to avoid where z equals 1 and z equals 2. So here, I just outlined in the overview slide the part for D1, and that's where modulus of z is less than 1. I take a look at my first fraction, 1 over z minus 1. I see that I can get it into this form over here if I multiply the top by negative 1 and the bottom by negative 1. And now I have the negative, and here I have 1 over 1 minus z is exactly this form, so I can put in my summation z to the n. Next, I look at the other part of my partial fraction, 1 over z minus 2. And the thing I notice when I compare these two, I need z added to the constant 1, not some random constant like 2, but 1. So what I do is I factor out the 2 from the numerator, so I get the minus 2 and then minus z over 2 plus 1. I kind of fully factor out the minus 1/2, change the order of this, and I have 1 minus z over 2. Now I can use this formula here, where I replace z with a simple function of z, and that simple function is now z over 2. So in my summation formula, I get z over 2 to the n, and I still have to carry over my 1/2. So what this means, also when I use this formula, I have to check that the modulus of z is less than 1. Otherwise, my series won't converge. So I did that here and also here. So here, when I'm checking my z, needs to be less than 1. And in D1, z is less than 1. For this portion here, what I substituted for z was z over 2. So I need to check that z over 2 is less than 1. And in D1, when z is less than 1, that will be true. And so I'm good. So what I can say is f of z, which is equal to minus 1 over z minus 1 times z minus 2 by partial fractions is equal to 1 over z minus 1 minus 1 over z minus 2 from my work is equal to, this part of the fraction is equal to minus the summation z to the n, and the second part, this part of the fraction, is equal to my minus 1/2, but now I have a minus here, so that becomes plus 1/2 summation of z over 2 to the n. Again, we'll go over this entire problem in more detail in the video. That concludes our overview, so now we can go back and look at the Laurent series in more detail and with more examples. We will start again by looking at the definition of a Laurent series. And the need for a Laurent series is that when you have a Taylor series, and this is what the form of a Taylor series expansion, your exponents or your powers on Z are all positive. So the Laurent series gives you the possibility then of having exponents where the exponents are negative or in the denominator. And the idea here is that the reason why this would fail to be analytic at some point is because of this division by zero, essentially. And so now the Laurent series gives us the ability to express a series that involves both positive and negative powers of Z minus Z naught. And the Laurent series theorem starts with, suppose we're first going to look at what the conditions are. So suppose the function is analytic throughout an annular domain. And so here I've drawn an annular domain. And the idea is you have Z minus Z naught. So here's Z naught, the center of our domain. And the distance between Z and Z naught is going to be greater than R1. So Z is going to be greater than this radius here. And this is dotted because we do not include the boundary. So it's greater than out here, but it's less than R2. So it's less than this second circle. So this annular region is this inside kind of what is shaded here in yellow, sort of like the donut shape. So that would be an annular shape. And sort of the idea of this annular shape is that if you have this point Z naught here, where you're in danger of having a zero, of having your function undefined, you make this radius R1 super small, just enough to enclose Z1, and then you have your curve somewhere between R1 and R2. Essentially, you make your domain everything but that one little point is the idea. Back again to the theorem. Suppose that we have a function that's analytic throughout an annular domain. So it's analytic in this yellow portion, centered at Z naught. And let C denote any positively oriented simple closed contour around Z. So something like this. But it has to lie in the domain. This should be kind of smooth here, no raggedy points. And it lies in the domain. So it lies completely in this yellow portion here. Then at each point in the domain, f of Z has a Laurent series representation, and it's given by this formula here. Our AN and our BN coefficients are given by this, but we're actually often not going to use this. But I'm also going to mention this analytic part coincides with the Taylor series portion. It is, if we don't have any principal portion, then we would have a Taylor series. And then when we have the principal portion, we have the negative exponents, and that would be a Laurent series. So a Laurent is sort of like an expansion of the Taylor series. And in particular, it's an expansion when we're in danger of Z naught being a singular point where f is no longer analytic because of this division by zero. We can find our first Laurent series by looking at the Maclaurin series we had looked at in the previous video. E to the z is equal to n equals 0 to infinity, z to the n over n factorial. I've rewritten that formula for e to the z, the summation z to the n over n factorial here. And now what I'm going to do is replace the z in this formula with 1 over z. And certainly that's a valid thing to do because if this formula is good for a complex number z, it'll be good for a complex number 1 over z, assuming 1 over z is defined. So then we have e to the 1 over z is equal to n equals 0 to infinity, 1 over n factorial, and now I have 1 over z raised to the n, which I just rewrote as 1 over n factorial z to the n, and then writing this out, expanding this out, when n equals 0, here I get 1. When n equals 1, I have 1 over z. When n equals 2, I have 1 over 2 factorial z squared. N equals 3, 1 over 3 factorial z cubed, etc. And you'll notice this series has no positive powers. So the analytic portion is 0, and it's fully all principal. And like we did for Taylor series, we're going to turn our attention to finding representations of other expressions, such as z plus 2 over z squared minus 5z plus 4, finding a series expansion. And as we did for Taylor series, we start off with a formula that we know. So we know e to the z is equal to z to the n over m factorial. We know that 1 over 1 minus z equals summation z to the n. We know sine of z is equal to the summation negative 1 to the n z to the 2n plus 1 over 2n plus 1 factorial. And then by taking the derivative of both sides, we get cosine, or term by term derivative. We get cosine of z is equal to summation negative 1 to the n z to the 2n over 2n factorial. And these formulas we developed in our last video. The next example is to find the Laurent series expansion of f of z equals 1 over z minus I squared. And this is sort of a trick question because this is already in Laurent series form, right? This is z minus z naught being I squared. You can also write this as z minus I to the negative 2. So this is purely principal form. There's not the analytic section, only negative exponents. You can write this as a series, n equals 0 to infinity, where it's Cn over z minus I to the n, where Cn is equal to 0, except when n equals 2. So in this way, you can see this more clearly that it is in series form. There just happens to be only one non-zero term. The next example is to find the Laurent series expansion of f of z equals minus 1 over z minus 1 times z minus 2. The first thing I want to do, again, I have this like polynomial over polynomial form, so it looks something like this, right? It certainly doesn't look like e to the z or sine or cosine. So I need to break this up, again, using partial fractions. I have the work down here, so I've copied my minus 1 over z minus 1, z minus 2, and I want it in the form of some number over z minus 1 plus b over z minus 2. What I do is I multiply both sides of the equation by z minus 1, z minus 2. On the left-hand side, that'll leave me with negative 1. On the right-hand side, when I multiply a over z minus 1 times z minus 1 over z minus 2, this will cancel out the z minus 1, and I'll be left with a z minus 2. For the b over z minus 2, when I multiply it by z minus 1 times z minus 2, the z minus 2 cancels out, and I'm left with b times z minus 1. I can multiply out then, multiply out the a, multiply out the b. Then I look, and negative 1 would have to be minus 2 minus b. I group my z terms. There's no z terms on the left-hand side, but on the right-hand side I have az plus bz. I solve these two equations. I find a is equal to 1, b is equal to negative 1, and therefore my fraction, negative 1 over z minus 1, z minus 2, is equal to a is equal to 1 over z minus 1, b is minus 1, so this plus becomes minus, which leaves me with minus 1 over z minus 2. The next thing we need to note is f of z has two singular points at z equals 1 and z equals 2. You can see that's where we have the danger of division by 0. So at this point, our function is not analytic. So our domain is then separated into three parts. There's d1 where z is less than 1, d2 where z is between 1 and 2, and d3 where the magnitude of z is greater than 2. And I have this drawn here in this drawing. So I have d1, which is inside the circle of radius 1. That's our first part of our domain. The second section of our domain is between the circle of radius 1 and the circle of radius 2. And then finally, d3 is the part of our domain where we're outside the circle of radius 2. And again, we have to separate our domain this way in order to avoid our singularities. And what I'm going to do, because this problem has three parts, right, for d1, d2, and d3, I'm going to make some space by clearing out this. I'm going to leave my formula here that I will be using, and then also my partial fractions, and the note about dividing up my domain into three parts. And we will start with d1, where the modulus of z is less than 1. And the two fractions I am working with is 1 over z minus 1 and 1 over z minus 2. I want this 1 over z minus 1 in the form of 1 minus z in the denominator. That's easy to do. I can multiply the top by negative 1, and then when I multiply the bottom by negative 1, I am going to get my negative 1 over 1 minus z, which now I can plug directly into this formula. I have the negative then summation of z to the n. But the thing I need to check in this formula is that the absolute value of z, or the function that I've replaced z with, is less than 1. In this case, the function I replaced z with is just z. I didn't do any replacement. It's exactly in the right form. So I need to verify that the absolute value of z is less than 1. And I'm good because in D1, I have the modulus of z is less than 1. So this is how I convert this first fraction. Now I'm ready to work on this fraction 1 over z minus 2. And now I want to put the 1 over z minus 2 into this form, 1 over 1 minus z. So the problem is this 2, because I don't want any random constant here added to z, or subtracting z from a random constant. What I want is the number 1. So I can solve this, put this in this form, by factoring out a 2 in the denominator. So I factor out the 2, so I get 1 over minus 2, and actually, because I want this to be positive 1, I'm going to factor out a negative 2. Then that will leave me over here with minus z over 2, and this will leave me with my 1. So you can see if I just multiply in the 2, I get my positive z, and then I get my minus 2. And then I can take out my minus 1/2, and I'm left with the form of 1 minus z over 2, which is exactly this form here where we replace this z with z over 2. When I do that now, I still have my negative 1/2 multiplying this, but now replacing in this formula, my 1 minus 1 over z is the summation n equals 0 to infinity z to the n. Replacing z with z over 2, I get summation of z over 2 to the n. And the last thing I need to do is check whatever I replaced z with, that is z over 2, that it's less than 1. If it's not less than 1, my series won't converge and I can't use this. So what I need to do again is verify that my modulus of z over 2 is less than 1. But that is true when we're in D1 and the modulus of z is less than 1. So I'm good here. That means my original f of z, over here my original problem statement, which is equal to minus 1 over z minus 1 times z minus 2, is equal to, by partial fractions, 1 over z minus 1 minus 1 over z minus 2. By my work here, my 1 over z minus 1 is equal to the summation, the negative summation, of z to the n. So that's what I have here in place of 1 over z minus 1. And then for z minus 2, that's equal to this summation here. And here I'm going to subtract 1 over z minus 2. So that's going to make this sign positive now. And I have my 1/2 summation z over 2 to the n. So this is my final answer for D1, which is this area here where z is inside the circle of radius 1. I'm going to put this line over here for my reference. So I'm going to make space now so we can work on D2. And now I'm ready to work in the second part of our domain where the modulus of z is between 1 and 2. In other words, z is in this yellow area here between the circles of radius 1 and radius 2. And again, I'm looking at the two parts of my fraction. I should be pointing up here, my 1 over z minus 1 and my 1 over z minus 2. For my first fraction, 1 over z minus 1, again, I want to put it in this form, 1 over 1 minus z. So to get the 1 positive and the z negative, I'm going to multiply the top and the bottom by negative 1. So I get minus 1 over 1 minus z. So now I can use my formula. So this is simply equal to negative the summation n equals 0 to infinity z to the n. And just like I did when I was working D1, I want to verify that I can use my formula that the modulus of z is less than 1. But now in D2, modulus of z is greater than 1, which means this series won't converge. So I can't use this. I'm going to kind of put a little X on it because I can't use this anymore. Maybe I won't X that. And again, this is different from D1. I could use this form in D1 because modulus of z was less than 1. But here I cannot use this form in D2. I'll need to do something different. I still need this to be the form with a 1 and a z. So here, essentially what I did is I tried to factor out the -1 to get this form. The other thing, though, that I can do is I can try to get this z to become my 1, and then this 1 to be my function of z. So in other words, I can factor out the z in my denominator, then my denominator becomes 1 minus 1 over z, right? So when I multiply this out, here I get my z back, and here I get my -1 back. But now what I have, when I factor out my z, so I have my 1 over z times 1 over 1 minus 1 over z. And this is exactly this form where I can replace this z with the simple function 1 over z. And this 1 over z here is just fine because this is in terms of powers of z. You'll see how that gets multiplied in later. So as I said, I'm going to replace z with z in this formula here, which I copied. 1 over 1 minus z is equal to the summation of z to the n. When I replace then this z with 1 over z, I have my 1 over z here, that's multiplied, times summation of 1 over z raised to the n. And now I can combine these two, so I get summation n from 0 to infinity, 1 over z, n plus 1. This here then is my summation representation of my 1 over z minus 1. And I can verify this function 1 over z is less than 1 because in D1, z is greater than 1. I shouldn't say z is greater than 1. Modulus of z is greater than 1. So now I'm all good, and I'm ready to work on 1 over z minus 2. I literally just copied my work from D1. So when I look at 1 over z minus 2, again, I don't want z combined with some random constant. I want z combined with 1. So I factored out my 2 in the denominator, and I got 1 over minus 2 times minus z over 2 plus 1. I fully factor out my minus 1/2, and here I'm left with 1 over 1 minus z over 2, which now when I plug into my formula, replacing z with z over 2, I'm going to have the summation, well, I carry over my minus 1/2, the summation of z over 2 to the n. And the last step, I want to verify this function z over 2 is less than 1, so that I know that my series will converge in this region. But z over 2 will be less than 1 in D2 because z is less than 2. I guess I should write in D2. So we're all good, which means my f of z, copying from my original problem statement, which is minus 1 over z minus 1 times z minus 2, using partial fractions is equal to 1 over z minus 1 minus 1 over z minus 2 is equal to, from our work in D2, our 1 over z minus 1, it was not equal to this because we don't converge, but it is equal to, where's our final answer? This over here. So I'm going to move that, summation n equals 0 to infinity, 1 over z n plus 1. And then for our 1 over z minus 2, there's a negative, so this is going to change this sign to positive 1/2, summation z over 2 to the n. And this is my final answer for D2. And I'm going to copy this answer over here next to my D2. I'm going to get rid of all my work so that I can make space for us to work on D3. I'm going to start my work similar that I did for D2. For D3, I have my two fractions, 1 over z minus 1 and my 1 over z minus 2. These are our two partial fractions. And initially for D2, I tried to multiply at the top by -1 so I could get the numerator in the form of 1 minus z and directly plug into my series formula. But what I found is in D3, modulus of z is greater than 1 because in D3, modulus of z is greater than 2. So I can't use this formula because it won't converge. This formula has the condition that modulus of z has to be less than 1. So then what I did is instead of essentially dividing by -1 or factoring out a -1 in here, I factored out the z. So my denominator becomes z times 1 minus 1 over z. Again, you can multiply out and see I still have the same fraction. I factor out my 1 over z, and I'm left with 1 over 1 minus 1 over z. This 1 over z will just become another power of z, so this is fine. Here now, I can plug into this formula, replacing z with 1 over z. I have my 1 over z here, replacing z with 1 over z in this formula, I get 1 over z to the n. Combining these two 1 over z's, I have the summation of 1 over z to the n plus 1. And again, I still want to check whatever I replaced this z, the simple function I replaced the z with, which is 1 over z, is less than 1. So 1 over z is less than 1 in D3 because modulus of z is greater than 2. So I'm good here with this summation formula. I'm ready to work on 1 over z minus 2, and again I copied my work from D2. So because I want this in the form of z combined with the number 1, not any random constant, I'm going to factor out my 2. So I get minus 2 times minus z over 2 plus 1 in the denominator. Now I fully factor out my 1/2, and I have 1 over 1 minus z over 2. So now I have this form where I can replace z with a simple function of z, which is z over 2. So when I plug in z over 2 into this formula, I get the right-hand side as the summation of z over 2 to the n, and I still need to keep my minus 1/2 as a multiplier. But of course, the problems come when we check if z over 2, what we replaced z with, is less than 1, and it's not, because in this case, we're in D3, where z is greater than 2. And now, like we did for D2, when we had this type of problem, we're going to, essentially, the thing is we need to have a 1 in this numerator. We can either get the 1 by dividing by z or dividing by the constant. In this case, the constant is 2. When we divided by the constant, which I think is the more natural thing to do, you can see we had problems. So now we're going to have to try to divide the numerator by z. So I factor out the z, and I get my z, and then I have my 1, and then minus 2 over z. You can see when I multiply this out, I'll get my z back, and over here I'll get my minus 2 back. And now I fully factor out my 1 over z, so I'm left with 1 over z times 1 over 1 minus 2 over z. So I can plug this in to my formula, and I'm going to replace this z and this z with 2 over z. So I have that notated in blue. So what I have is my 1 over z times my summation of 2 over z to the n. Now I can combine this 1 over z with this 1 over z, so I get summation 2 is still raised to the n, but now my z is raised to the n plus 1. And I can verify that what I replaced z with in this formula, which is 2 over z, is less than 1, because in D3, z is greater than 2. So now I'm good for this portion of D3. And now, because I'm out of room, I'm just going to write my solution here for D3 directly on this line. So in D3, when modulus of z is greater than 2, and that's this outer region here, I forgot to tell you I had updated my drawing. So f of z, which is equal to minus 1 over z minus 1 times z minus 2 by partial fractions, is equal to 1 over z minus 1 minus 1 over z minus 2. From our work, 1 over z minus 1 is equal to this series here, n equals 0 to infinity, 1 over z n plus 1, and our 1 over z minus 2 is equal to this series here, and we're subtracting it, and the series is n equals 0 to infinity, 2 to the n over z to the n plus 1. And I'll go ahead and clear out all this extra work here, just so that it's not so cluttered, and you can now see our solution for D1, D2, and D3. This next example is kind of interesting because it's the first one involving sines. So we want to expand f of z equals sine of z over z squared at z naught equals 0. Remembering that, we're trying to expand to a power, a series of exponentials of z, we can factor out our 1 over z squared. and then we're left with sine of z. But we know how to expand sine of z. We derived that formula in our last video, and that's a summation of negative 1 to the n z to the 2n plus 1 over 2n plus 1 factorial. So this is a correct answer, but I went ahead and then expanded my summation here, and it should look familiar from, I don't know, first year calculus. 1 minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7th 7 factorial, etc. So it's the odd powers alternating signs, and then I can multiply everything by 1 over z squared. So this is my final answer. To review what we have done in this video, we covered Laurent series, which much like Taylor series gives us a way to represent a function in terms of a polynomial with both positive and negative exponents on our variable z minus z naught. The Laurent series says suppose a function is analytic throughout an annular domain where z minus z naught is greater than r1 and r2. And remember, at this point, z naught may or may not be analytic. So the idea is we're going to surround our singularity z naught with a very small circle, infinitesimally small r1, so that we can isolate that singularity, and then we can call the space between the circle of radius r1 and r2 our annular domain, so where we are analytic. Then we let C denote any positively simply closed contour around z naught lying in the domain. Again, now this blue curve C, for example, is lying in the analytic portion, which lies between the circle of radius r1 and r2. Then at each point in the domain f of z, we have a Laurent series representation given to us by this formula. F of z is equal to n equals 0 to infinity, a to the n, z minus z naught to the nth power plus the summation n equals 0 to infinity, b to the n over z minus z naught to the n. This part here, where our exponents are positive, and you can see we are not in danger of division by 0, is the analytic portion. And when the principal portion, this part over here, is equal to 0, this analytic portion is exactly the Taylor series. When we do have non-zero principal part, in this case we can have negative exponents on our z minus z naught, or essentially z minus z naught in the denominator, and we can potentially now have singularities. Here are our formulas for the coefficients for the analytic part. A sub n is equal to 1 over 2 pi I, closed curve integral f of z dz over z minus z naught n plus 1. And the coefficients for bn, the principal part, is 1 over 2 pi I, closed curve integral f of z dz over z minus z naught minus n plus 1. We had our first example of a Laurent series. We took the Maclaurin series from our previous video. E to the z equals summation z to the n over n factorial. We replaced the z with 1 over z. So now we have e to the z equals n equals 0 to infinity, 1 over n factorial z to the n. And when you expand this out, you'll notice there are no positive powers of z. This is purely principal. Well, there's the 1 here. But this is purely a principal Laurent series. And much like Taylor series, actually even more so than Taylor series, we try to avoid using these integral formulas to calculate an and bn. Instead, what we do, if we want to know the Maclaurin series expansion, for example, of e to the z, we look at some of our known functions. We know that e to the z has this series representation. We know that 1 over 1 minus z has a particular series representation. We know the series representation of sine of z and cosine of z. So we'll compare our function, in this case e to the 1 over z, for example, and we'll look to see what most closely fits. Well, it's not sine or cosine, it's not this polynomial over polynomial, it's obviously e to the z. So we try to convert e to the z and make it look like the function we are trying to represent, in this example, e to the 1 over z. And the things we can do to modify these formulas is, 1, replace z with a simple function of z. In this case, the simple function would be 1 over z. Multiply the entire equation, both sides of the equation, by a value. Term by term differentiation, And again, this is how we got the cosine formula. And last, making adjustments to summation indices. We have this example here, the Laurent series expansion of f of z equals minus 1 over z minus 1 times z minus 2. It was somewhat involved. First, we broke up our fraction into 1 over z minus 1 minus 1 over z minus 2 using partial fractions. We then noted that f of z has two singular points, z equals 1 and z equals 2. So we separated our domain into three parts in order to avoid our two singularities. The first domain, d1, is modulus of z is less than 1. d2 is modulus of z is between 1 and 2. And d3 is modulus of z is greater than 2. In this overview slide, I only have the work for d1, and that is when modulus of z is less than 1. Our first fraction, 1 over z minus 1, I can get it into the form here. Polynomial over polynomial by multiplying the top by negative 1, the bottom by negative 1, and now I can factor out my negative 1, but here I have 1 over 1 minus z, which is exactly this form, which has the series form of summation z to the n. And again, there's a negative in front because of this negative 1 here. For our next part of our fraction, 1 over z minus 2, in this case, because we need z combined with the 1, we factored out the 2 in the denominator. So then we have my minus 1 half times 1 over 1 minus z over 2. This is exactly this form where we replace z with the simple function z over 2. So we have on this right-hand side z over 2 to the n. I keep my negative 1 half. And then finally, my f of z then is equal to my 1 over 1z, which is our minus summation z to the n, minus this summation, which makes it a plus 1 half summation z to the 2 over n. At this point, sometimes I give you some review problems. I give you 4 problems for you to try. Pause the video, you try it, and then I'll give you solutions. Because this video is already getting kind of long, and because some of these solutions takes, I really do feel like I should go through the explanation, and they'll take a while. What I'm going to do is I'm going to give you the problems in this video, and my next video, I will solve these 4 problems for you. So the first problem is to expand f of z, which is equal to 1 plus 2z squared divided by z cubed plus z to the 5th. The second problem is to expand h of z is equal to z times cosine 1 over z. The third problem is to find the principal part and the residue b1 of f of z equals z cubed plus z squared over z minus 1 squared. And the residue b1, that's going to be your first coefficient in this in your Laurent series. So it's your first coefficient in the principal part. It's this b1 over here at z naught equals 1. And note your formulas for e to the z and 1 over 1 minus z and sine of z and cosine of z are centered at z naught equals 0. So you'll need to do something here to adjust. This is kind of this will take some thought. So don't feel bad if you don't get this one. You can look at my solution in the next video, but do give it a try. And finally, the last problem is find the Laurent series expansion of r to the z equals z plus 2 divided by z squared minus 5z plus 4. As I mentioned, in my next video, I will solve those 4 Laurent series examples for you. So that's it for this video. Thank you for watching.